Recording. All right, so today we are going to continue from where we left off last week. Just a moment. Yeah, so today we are going to start off, continue from where we left off last week. Now, in last week, we dealt with just a minute. Yeah, so last week we dealt with support vector machines. We looked at the theoretical foundation and everything that we needed to know in order to apply those principles in machine learning model development. So I'm going to open okay, so let me share my screen. Okay, so based on our schedule, this is what we worked on so far, and we ended up at the support vector machines. Today we are going to look at naive Bayes, and of course, if there's time, I'll try and combine these two KNN classifier, so that's at least you have that too. And on Friday, we'll touch on the few things that will be left out, and then hopefully next week we'll move on to other things that we needed to look at. So we are looking at naive Bayes.
Can you give me 1 minute? So what we have here now, these are predominantly the basic supervised classifier algorithm or classification algorithms. These are the algorithms that are used to perform tasks that are based on classification. Okay, so anytime we have some solution of a sort, then we have to decide the solution that we want to provide. Which type of task are we interested in performing? The moment we start thinking about classification, then we can use any of these algorithms to perform the task for us. Now, one of the important things that I want us also to know, especially for those who are using machine learning for further works or projects, each of the algorithms here, they have their, at least by now, what I've been going through with you. By now, you know that each has what it calls its key strengths and then weaknesses. Now, so when we have to develop a solution, we don't close our eyes and say, okay, I want to use decision tree. What will inform your decision to say that, okay, I think decision tree will be the best algorithm that I can use to do my classification task. So most of the time, what we do is, once we know the common or the popular supervised learning algorithms, we test each one of them on the data that we have. We talked about the data being split for training and then training task, and then also for the testing task. So we want to test each one of them to see whether and monitor each algorithm, their performance. We monitor two types of performances. One is ability to learn the patterns in the data, including noise. And then we test with our test sample, the model. So we learn the patterns to formulate a model. And then we test the model with test data to see whether the model is working well. I'm also sure that some things have been mentioned to you in terms of what we call overfitting and then underfitting, or overtraining and undertraining. These are real problems that happen when we are dealing with what we call machine learning model development for solutions. Okay. So one of the weaknesses we have with decision tree, I'm sure by now you have been told, this has to do with the stability when it has to do with classification. So when you have the task, you don't just get up, so I want to use it. You please take note of the data you have, and then you test each of the algorithms, the common algorithms that are used in trying to solve that problem. And then you monitor each of them. Echo, please, can you mute? And then you monitor each of them to know which of them is giving you the best performance. Alice, Ken, please, have we dealt with performance measurement?
No, sir. I believe maybe right after today, that's we'll complete these algorithms. We can touch on that before we proceed to.
Okay, all right.
Yeah.
So we test each model, then we can now pick out the best performing model based on the algorithm that we have tested. And then we can say that, okay, this is the best algorithm, and you have your report to show that this is the best that can support the work that you are doing. So this is what we do. So whilst we are going through, please take note that these are the popular algorithms, support a single supervised learning algorithms that are used. There are others that we may get along as we go through, and I will deal with combining algorithms. For example, can we combine support vector machine and KNN to solve a problem? Those are things that we'll deal with when we come to ensemble learning. Okay, so please, if you have any comment or questions, let's raise them up, and then we'll go through with you on that. So Ken, I hand over to you there.
Okay. All right, thank you very much, Dr. Mills. So today we are going to look at the naive Bayes and then the KNN, that's the K nearest neighbor classifier. And then just as Dr. Mills mentioned, I think we should also elaborate a little bit more on the performance metrics and analysis. And I believe if there's time, I'll drift into that and then touch on a few things that I was reflecting and felt we might have left off. So what I'm going to do is I'm going to open up this and see what we get over here. Let me close this. So I'm going to open up my Jupyter Notebook environment. And there's a brief presentation I'll do regarding some basic theoretical concepts that we are going to learn. Most of the time, I tell students, when it comes to these traditional machine learning models, a little bit of the theoretical concept is needed, and then the rest is you using the library and changing or tweaking the matrices that exist in order to get optimal performance from the algorithm. So what I have over here is yeah, a short presentation. Let me just clear these ones. All right. So quickly, maybe in the next 10 minutes, I'll be done with this one. But obviously, we're going to look at the naive Bayes. And the naive Bayes is an interesting one because there's a little bit history to this. And it is actually named after Thomas Bayes, who was a I believe, a Presbyterian minister and also a statistician, who lived so many years ago. Nowadays, you don't find that with a lot of our pastors. So we are going to look at the introduction, some theoretical foundation, and the mathematical foundation that supports this algorithm and why we are even using it in the first place. So the naive Bayes is a probabilistic machine learning algorithm used for classification tasks. So earlier on, when we were dealing with the SVM and also the decision tree, we made mention of the fact that, well, for those ones, we can use them for classification and regression. And at the time we were exploring them, we only looked at classification. Later on, we are going to look at regression. But then with the naive Bayes, we're only looking at classification. And there's something interesting I've highlighted over here, which is it is a probability or a probabilistic machine learning algorithm. So the fundamental mathematical concepts or foundation of the naive Bayes is based on the Bayesian theorem, which is also based on probability. So we are looking at probability. Now, it is based on the Bayes theorem or the Bayesian theorem, which provides a way to calculate the probability of a hypothesis based on prior knowledge. So, basically with what happens with probability most of the time when it's being taught in school is we are rolling dice or we are drawing a card from a deck of cards and all that. Okay, so let's just look at we having that deck of cards. Okay, and most of us are males. We probably have played cards before, so there's something we can relate to. So with a deck of cards, we have let's say 4 classes. Okay, back in where I'm coming from, the classes are like the hearts, okay, the spade, the diamond, and the other one. Okay, like I said, where I come from, we call one Kalu and those things. So those are the classes. Just trying to infuse a little bit of machine learning in here. All right. Now, with those classes, we are saying that, okay, we can use the Bayesian algorithm to actually predict a class. Okay, let's say I blindfold you, or maybe I turn the back of the card facing you, and I pick a card, and you can make a guess using probability. So the question is, okay, we are saying that with the Bayesian theorem, the naive Bayes is based on the Bayesian theorem, which provides a way to calculate probability on a hypothesis based on prior knowledge. So the prior knowledge is very important in a sense that we know that the deck of cards, each class, in this case, the heart of spades or all those things, each class has, I think, about 8 members each. So the prior knowledge is, if, for instance, I've removed 5 of one particular class, maybe the black spade, okay, if I've removed 5, then that means I'm left with 3. Now the question is, what is the probability of 3 out of the overall? So the probability of that 3 out of the overall is then going to be, if the cards were not replaced, then that definitely that's going to be what is left, which is the sample I have in there, divided over, by the sample space. And I hope that makes sense. So based on that probability, we can know that, okay, this one is left and things like that. So there's a formula that we are most interested in. And there's a simple way to look at this. Now, what's happening over here is we are saying, okay, the probability of A given B, okay, the probability of A given B is equal to the probability of B given A multiplied by the probability of A or divided by the probability of B. Now, there's some mathematics, maybe at some level, if you are doing these calculations by hand, you need to chew and pour, but then at the end of the day, you don't need this if you are actually doing machine learning. But the whole point is we are using the concept of probability to know, okay, this is how much we have left in there. So if I have 10 cards, and let's say I have, let's say, 2 classes, black and red, and I have 2 reds and then 8 blacks, and I pick one, the probability that that card is red is the number of reds I have over the sample space, which is so probably a 1/5. Okay. I mean, if you definitely 2/10, but then when you track it down, it's 1/5, which basically also tells you that out of every 5 cards, randomly, you have 1 card being that your class. Now, when you have that and you train a system with it, okay, your machine learning model, and now you present a new data in terms of making predictions, it is able to look at that knowledge that, okay, based on the data that was received, based on the data you used to train me, I know that, okay, the probability of any new feature coming in based on the prior knowledge I have with the training that has gone on could be this. And that's why your sample space and the distribution of your classes in terms of the balancing should be up there, because if there is an imbalance, definitely is going to affect your prediction one way or the other. Imagine there's an imbalance of let's say 80-20 in terms of 2 classes. Clearly, then the model is going to be biased towards the majority class, and that's where we may want to do some analysis to figure out why certain things are happening and how we can correct them. All right. So there are some few descriptions of the parameters that we have in the formula, which we are saying, okay, what we have over here as A, probability of A given B is the probability of event A happening, given that B is true. That is the posterior probability. And now the ones that we see over here is the probability of B given A, and the probability of B given A, and the probability of, B given A is the probability of B happening, given that A is true, or the likelihood is high in some regard. Because at the end of the day, the probability is not always going to be 100%. So there's always some marginal, maybe a 0.5 or a 0.7, some way of somehow. And now the probability of A, or the PA, is going to be the probability of event A being the prior probability, and the probability of B being the event B. Now, in terms of what we would understand very well, trying to relate this to machine learning, is let's say, okay, let's have a scenario where we want to classify emails into, let's say, spam and not spam. Okay, so we have 2 classes over here. There's a binary classification problem, and there's a very good fit for using Bayesian theorem or naive Bayes. Now, what happens is, okay, with the naive Bayes, because it is probability, and let's say we have a very good data set, which is fairly balanced, which has extracted all the features from a spam mail and a non-spam mail or a not spam mail. We have all the features. So we are saying that, okay, so given that we have a class label, let's say CK, which is 1 class, and the inputs are what we have over here. So the X are the input features. So maybe it is the IP address that is sending the mail, or maybe some text in the mail, okay? And of course, there are some easily identifiable spam words. Congratulations, you won. Those words will be flagged as some features that we want to look at. But then I think things like maybe the IP address, the frequency of maybe that mail being sent, and some words in there. So we gather all that features into our data called X, okay, where the X1, X2, X2 are the features. So now we are saying that the probability of the class spam given a feature X. So this X will include all the features I just spoke about. So it's almost like a 1 rule, okay, or 1 instance of that particular data set. So we are saying that, okay, the probability that this data set that we have provided belongs to a spam class is going to be equal to the probability of that feature, given that it is a spam, multiplied by the probability of the spam. So obviously the probability of spam, if the data that we have is fairly balanced. Probably maybe the probability of the sperm will probably be maybe 50%, okay, or a 0.5. Now the features will come in, and those features are also going to have some matrices, and we are going to say, okay, the probability of that feature, given that it is in the sperm class, we are going to multiply with the probability of sperm, all divided by the probability of feature. And at the end of the day, it's going to be numbers that's going to be divided. And whichever number that we have, okay, if it is falling below a certain threshold, then we can say that, okay, it belongs to that class. If not, then it belongs to the other class. So that's basically that. And this is something that's going to help us understand if it is just for a binary classification. So in that sense, the system can look at it as, okay, the threshold is maybe a 0.5. If the threshold is a 0.5, what that means is if we fall above a 0.5, then it is in that class. If not, then it is not in that class. So there'll be that classification one way or the other. All right. Now let's quickly move back to where we are actually going to implement this in code. And today what we are going to do is, yes, I prefer to always use the iris data set because that's some data that we already know. Now, remember, most of the things you do in machine learning, I believe about 60% of the work probably would have to do with the data preparation. Because once you have a very good prepared data set that you understand really well, the rest is just using a library and just putting in your data, and then you do model of fits or whatever parameters that you have, and you are good to go. So we are going to do one with the iris data set, and today we are also going to do another one with a breast cancer data set, also in iris, okay? Oh, sorry, also in scikit-learn, and I believe that will give us a different perspective, and also more or less something that the biomedical engineering students will relate more because of that particular example. So we are going to run the usual import. So I'm going to say from sklearn import data sets. Then I'm going to say from sklearn dot metrics. I would want to import accuracy score. Then from sklearn dot I think the other one that we need is, okay, model selection. I would want to import train test split, and so we have our data set. We have, yeah, I think we are good to go now. So let me just run this, and I'm thinking about something. Yeah, I'll bring that along later on. So let me just import get in here, import pandas as PD. Today I'd want us to visualize things very well. So I'd want us to have a data frame and see how things look. So we have this, then of course let's bring sklearn dots, and this one is going to be the naive bay. I want to import the Gaussian naive bay, which is Gaussian NB. So this is how scikit-learn calls that particular library. But then one other thing I also failed to mention is the fact that with a naive bay, there are lots of variations to it. Okay, so it basically deals with the probability distributions. Okay, so let me just do a Google search. Probability distributions. So there are a lot of probability distributions. There's Poisson, there's Bernoulli, and a host of others. Okay, let me just do a list of. Maybe let me just, okay. All right, so yes, so these are the common ones. Okay, there's Bernoulli, there's uniform. The uniform is also, yes, then there's binomial, the normal, the Poisson, and the exponential distribution. And over here with the Gaussian naive Bayes, we are going to look at the normal distribution. So the normal distribution is what, if you are to plot it on a graph, is going to look like this. It's going to look like yeah, it's going to look like the bell shape this way, okay, with that curve, okay, and at the very center is going to be the mean, and the distribution, the standard deviation from wherever point you have to the mean, I mean, it should be equidistant if it is perfect, but sometimes we are never going to get it perfect, but at least if anything looks like this, we look at it as the normal distribution. So over here, what's Bernoulli, what's naive Bayesian is, we are going to rely on this normal distribution. And with a normal distribution, one of the things I also want to let you know is that with a normal distribution, we are most interested in two main parameters. Okay, the first parameter we are looking for is the mean. So we want the mean, and also we want the standard deviation, which is our SD. Okay, so we want the mean and the standard deviation. And the reason we want the mean is, once we have that graph, we can clearly tell that, okay, at the center is the mean, and the standard deviation is where we are measuring, okay, how dispersed are we from the mean, okay, the center. Now, what I want to also show you, just do a quick Google search, is to also prove a point over here that, let me see, the normal, or let's do Gaussian. I mean, it's the same thing. Gaussian distribution, let's say, do a curve, okay? So that's exactly what we see over here, which is also known as the normal distribution. So it is basically the same, and that's the bell curve. And this is what I was saying, that the two key things we need over here is a mean and then also the standard deviation, as we can clearly see over here. Because in that formula, the function is giving us 1 over the mean root 2 pi raised to the power e, okay, that raised to the power negative 1 over 2 all over the feature minus the mean, all divided by the standard deviation square. All right. So I believe these formulas, based on the level of mathematics that we've covered, right from elective maths, I believe we've seen this before. All right. Now, the reason this is very important is that the mean and the standard deviation is what makes the key decision, okay? So now let's look at this from this angle. Let me just put it out over here. Assuming what we see over here, let's assume, okay, this is just some assumption I just wanted to make. So this is a mean, this is a middle point. If it is, for instance, maybe a binary classification, let's just assume to this side, okay, is, let's say, one class. So let's say C1, and everything to the right side is, let's say, another class. So let me do C2 over here. Let me clean whatever thing we have. Now we can make predictions based on the means and the standard deviations of some features that we get. And let me give you a typical example. So let's say in a typical, let's say, a level 200 class, okay, or maybe a typical level 100 class, the mean age of students, if I'm not mistaken, will probably be around, let's say, I was going to say 19.5, but let me just round it off to 20. Because most students will be around 18, 17, and then you may have some 20s or some mid-20s around, okay? So this is the mean age for an undergraduate class. Now the question is, maybe I walk into a class and I ask, today we are going to take attendance. Is everybody in class? Then everybody says, yes, sir. And then somebody raises his or her hand and says, oh, sir, please, there's one person who is not in class. and okay, I'm taking the attendance, and maybe I need some extra information. I need the data of maybe the age. So I take attendance and take age, and maybe the VC is waiting on me to present that data for her to do some work with it. And I need to bring that forward. Now, I can make an intelligent guess and say that, okay, the average age or the mean age of the class is 20. If I pick an age of, let's say, 20, well, I haven't done so much bad. I can do the calculation and now look at the standard deviation. How wide is the, for instance, the youngest person of the class? Okay, maybe the youngest person of that class is about 16 years. And the eldest person in that class is about 24 years. So to my right, I have 4 over here, 4 points to my right, and also 4 points to my, to my left and also to my right. So the standard deviation is 4 and the mean is 20. Clearly, if I pick anything between 16 and 24, I'm within range. But then if I pick, let's say, 21, then I'm very close to my mean, because the mean basically means majority of people within that particular sample space are within there. And that's basically what we are dealing with when we are dealing with the normal distribution, because with the Gaussian or the normal distribution, we are most interested, or the most interesting parameters that we look out for is the mean and the standard deviation. So it says the probability density of a particular feature will look like this, and the varying parameters is going to be the mean and the standard deviation. So now let me just clear this one and proceed on what we are dealing with based on our classification. So what I want to do is, so what we have over here is, yes, we have the Gaussian naive Bayes, okay? And like I said, there are different variations of it. So I don't have them off head, but then let me just once again check over here, because IntelliSense may help me with this. So if I'm to do from this time around from sklearn dot naive underscore b, okay, let me just do this, import naive b. Now let me do naive b, and let me see the options I have over here. Okay, it says, okay, no problem. Let me do naive b dots. All right, so you could see that we have the Bernoulli, okay? We have the categorical naive b. If you are dealing with categorical data, I think this will be your best bet. Okay, you have some zeros and ones, and you want to build a system that will be more rigor and very intentional about that particular data, then you are looking good. Now, this is what we are dealing with, or we are going to use. That's the Gaussian naive Bayes. And then there are some other ones that the multinomial and a lot of other ones. Okay, I believe those are the ones that we have over here. All right, so we are not only limited to the normal distribution. Okay, we can look at other things, but some of those other things is also going to be dependent on, one, the data set that you have, and also the kind of distribution you are trying to project based on some analysis or even some visualizations you have done. All right. So now that we know this, okay, now let's proceed. So we've done our imports and we have everything going. So now let's bring in our data, and this is something we've done over and over again. So let me just do data sets dot load underscore iris and call this method. And now when I do a preview of data sets, we have these data sets that we know so much well, okay? And these are classes and some descriptions of things over here. So now let's try and decouple things into its rightful place. So I'm going to do X inputs as I always do, and I'm going to say data.data. Once again, this is a dictionary, and we are just trying to grab the X, okay, which is going to be the sepal length, sepal with CM, petal length, petal with CM, and stuff like that. So we have data over here. And now if I'm to do a preview of this X input and run it this way, that's exactly what we have. Okay. Now let's just concentrate on the Y as well. So let's do a Y underscore output, and that's going to be equal to data.targets, because that's the name of the target variables we have over here, okay, in this particular array. So data.targets, and when I run this, once again, let me do a preview to double check on everything. And this is what we have. So clearly everything looks good. Now let's do the splitting, which we've come to appreciate. So I'll copy this and I'll do my X underscore train, my X underscore test, and then my Y train, and then my Y underscore test should be equal to this function we are using to decouple everything we have over here. And what we are going to do is we pass in our X inputs and then our Y output. Let me type it out. Then we specify a test size of our choice. But the general rule of thumb is maybe a 30% for the testing will be okay, and then majority 70% will be for the training. So I'll run this and we are good to go. So now let me just do an inspection of everything to check if everything is okay. So yes, I'm expecting to see 105 okay samples over here. That looks good. And the X test is definitely going to be a 45 sample. All right, so that's looking good. And the number of features are also showing up over here. Let me do a Y train, which I can just print it out. Okay, so this one looks good. And the Y test, that one too is okay. All right, so let's build the model itself. So in the model, we are going to use this Gaussian naive Bayes that we've come to appreciate. So I'm just going to say the model is going to be equal to this, and we instantiate it this way just by bringing or building what I always call the skeleton of it. So just by doing this, it says Gaussian naive Bayes is not defined. Oh, okay. Why did I not run it over here? Let me run it again. Oh, okay, so it's naive underscore Bayes. What is happening? It says SK Gaussian NB. Cannot import name Gaussian NB. Oh, let me check from here. So naive Bayes dot Gaussian NB. Okay, I don't know why. Okay, somebody's in the chat. Okay, the spelling. Okay, let me check the spelling. Which part of the spelling, if you can help me? Naive. Okay. Oh, okay, AU. Oh, okay. All right. All right. So, I mean, some of these things happen. So let's run this and then run the other ones as well. So, and because I copied, it is reflecting here. Okay. So now the skeleton is built. So now we can now do the fitting. So now if I do model.fit and then passing my training bits of the data. So X train, Control C, then my Y train coming in here. And just about this, the training is done. Okay, so we have this model that we can make predictions out of. So I can do model.predict. And then what we need is to do with the, how do you call it, the X test. So I'll do a Control C over here, put this in here, and call this Y underscore predicted. So that's going to be this. I ran this, everything looks good. Now let me just do a preview of this. Now this is where I want us to pay attention really well, because I mean, I've said this over and over again, and I just want to reiterate because I believe from here, based on our plan and our schedule, we definitely have built a lot of models. So that experience will be there. So other ones we just touch on a few things and then move quickly. But then what I'm interested in is okay, so with what we see over here, we have ended up building this, and let me just have this. Okay, so I mean, I'm fan of doing this, and I think it's a very good thing because it makes me visualize exactly what I want to show. So these are original data sets we had this way, and then in that data set, what we ended up doing was okay. We had some X inputs, okay, and some Y, which were our labels. So iris setosa, iris versicolor, which were represented with those categorical data 0, 0, 0, 1, 1, 1, and stuff like that. All right. Now, what we ended up doing was okay, we split our data, and let me use a different color to make this conspicuous. So we split our data this way, and this was the 30%, and here was the 70%. Now we said, okay, this was the training part, so we call this X test. So once again, let me just type this down. We had this as X underscore test. Sorry, S string. We had this as X string. Okay, this portion, and then sorry. Oh, let me just clean this up. Okay, so we had X string, which is this portion of the data, and then we had our X underscore test over here, which is this portion of our data, the 30%. Okay, and this was, I mean, was going to be a Y train and a Y test. So let me just put that one also here. We have a Y train, and down here is going to be a Y test. Okay, so now what we ended up doing was okay, so we built a model, and in that model, as we can clearly see here, when we were fitting, we said model.fit X train, Y train. So we use the X train, which is this part, and also the Y train is supervised learning. So we needed to provide the lab, I mean the data set and its corresponding labels, okay, as the teacher. And after building that model, we now came to do a prediction. And with a prediction, we're bringing in X test. So this is the X test. And this X test went through the model and it has made some predictions you are saving as Y test, Y predicted. Now, what we are going to do is we are now going to compare this Y predicted to the original Y test. So now if I'm to come in here and now do a preview of the Y test, we get these values showing up over here. Clearly, some of the predictions were okay. I think there'll be some few that will not go well. Let me just clean everything I have over here so that we can make sense out of what we see over here. So over here, just at the back of this, I'm not seeing anyone, but then let me see. We have 111012220. Okay, I think this accuracy is looking pretty much great over here. You have 2221. Oh wow, this is almost giving us 100%. But then we can verify. Okay, so what we see in here is that we can check the accuracy score. So accuracy underscore, and then let's pass in this Y predicted and then the Y test. Okay, so we got 100%. Okay, that's not too bad, but then it raises question for further interrogation. Okay, if you are scoring 100% all the time, it cannot. Yeah, so at least this is what we have. But then what I wanted to show was, okay, so let's put this in a structure that kind of makes sense, because in some presentation of your data, you also need to make it very obvious for people to see exactly what was the actual and what was predicted. So what I want to do is, okay, I want to create a data frame, okay, and pass these values in there side by side, so that at least we can do that cross-checking with our eyes. And that's why I ended up importing pandas. Okay, so I can bring in PD over here. So I'm going to say the data frame is going to be equal to PD dot data frame. And what we are going to do over here, we're going to create a data frame of a dictionary. And that dictionary is going to have, so because it's a dictionary, that's why I have these curly brackets. Okay, so the key value pair. So the first key I want is the predicted. Okay, and its corresponding value is going to be the actual predicted. I'll do a comma, and then the other one I want is the Y test. So Control C, and then its corresponding value is what I see over here. So at least this one looks good. Now, if I do DF, I have it showing up over here. So the keys were just going to be the label names. Okay, that's what you have over here, and the actual values are what we pass in here. So over here, if you are to make a case in terms of a presentation of anything of that sort, we can say that, okay, well, this was the predicted and this was the actual, based on whichever we want to explain it. So we can actually make this something like predicted and actual, like you find in a lot of books out there. So these were the predicted values and these were the actual ones. Okay, so clearly everything looks up clean over here. Okay, and this is good. Now, let me briefly touch on the other performance metrics that we may want to further investigate. And this is very important. So what I want to do is we want to have a classification report. Okay, and classification report is also inside of this matrices. So in addition to the accuracy score, we can get classification report. So what I'm going to do is, let me just come down over here, and I'll say from sklearn dot these metrics, I want to import the classification underscore reports. So I'll run this. What am I getting? It says cannot classification. Okay. All right. So I have my classification report over here. So let me call this C underscore R for classification report and bring this out over here. And as always, you'd always want to be checking your predicted with your actual. So let's bring in the predicted over here. Control V and the Y test. Now, when I run this and do a preview of my C underscore R, I get something that doesn't look pretty much interesting for now. But then let me just wrap it up in a print function. I don't know why it happens this way, but then when you put it in a print function, it looks a little bit better in terms of how it's supposed to be presented. Now, because everything is 100%, I'll defer some of the explanations, okay, to when we build, let's say, for instance, the KNN, and maybe there are some slight variations, then we can make meanings out of, okay, why this is happening so. But then let's analyze the reports and see what we have over here. So in addition to accuracy, because this accuracy, we haven't even explored, okay, so the accuracy was given us 100%, okay. So this accuracy is good, but then sometimes we want to look beyond accuracy and look at other things. So the example I always give students is, let's assume you're a football fan. I know most of you are, and I, for one, I'm an Arsenal fan. So unfortunately, last week we couldn't win, but Arsenal played a match, and I didn't watch the match actually. But then maybe I get the news that, oh, we won. No, let me use this example because most of you relate. Chelsea. So Jackson scored 3 goals. Maybe you didn't watch the match and you just hear the score and Jackson scored 3 goals. You'll be very happy. Chelsea ended up winning 3-0. But then you meet somebody who watched the match and be like, Jackson didn't do well today, cry. And you be like, but he scored 3 goals. So the accuracy is only telling you one side of the story, how accurate he was in terms of scoring the goals. But imagine the person tells you, well, in that game we had 10 penalties and he could only score 3. That will give you a different perspective about his actual performance. Because just hearing 3 goals made you happy because you won by 3 goals to 0. Oh, it's a hat trick. He did very well. But getting the full report of him missing 7 and scoring 3, if I was the coach, the next time we have a match, we'll probably may not even end up getting 10 penalties, maybe just 1 penalty. So I'll be very cautious with who I put behind the ball. Okay. So beyond accuracy, we want to test for other things. So in the case of the Jackson example I just illustrated, in addition to how accurate we were, we also want to check for how inaccurate we were. Because if we're accurate 3 out of 7 and inaccurate 7 out of 3 out of 10 and inaccurate 7 out of 10, I'm definitely not taking that as a good performance, honestly speaking. And I believe most of you will not take that as well. So having said that, we need to look at what these ones means, okay? Because precision is, obviously what it suggests, okay? It is basically telling us how accurate we were. The recall is more or less telling us the opposite of precision, how inaccurate we were in some instances. Now, we have something we also call the F1 score. And the F1 score is the harmonic mean between the two. So I want to put the two together, okay, and divide it by 2. That's the mean. To actually know exactly, okay, so if you played 10 penalties, scored 3, and then you missed 7, probably your harmonic mean is not going to look that good, okay? But at the end of the day, you want to have that holistic perspective. Now, this support you see over here is very important. So you see that clearly we have 0, 1, 2 showing up over here. Now, when the splitting was being done, remember this report is coming in from the X test and the Y test. And the X test is definitely going to contain instances where, for instance, the Y test is going to contain instances where we had that sample from class 1, that sample from class 2, and that sample from class 3. So what this one shows basically are the classes. And the support you see over here is that, okay, out of the 45, because X test, the number of instances we have there is 45. Okay, if I'm to do, Y test, I keep on saying X test, I don't know why. And if I'm to do the shape, we are getting a 45 inside because that was 30% of 150, which is 45. So we are seeing that out of the 45, and of course we can sum these ones up because you see that at the end of the day, we are having 45 showing up over here because that's the total. Now we are seeing that out of that 45, 13 of them randomly selected were from class 0. 14 of them randomly selected were from class 1, and then 18 of them randomly selected were from class 2. In this particular instance, okay, where 0, 1, 2 are representing iris setosa, iris versicolor, and those ones that we know. So over here, it is then for us to make a decision based on, okay, if we ended up splitting randomly, and this is done randomly, okay, so you may have instances where it may even be skewed in terms of how many classes were used in the training. Because imagine if each class, we know the original data set had, I think 50 for each class. Okay, the original data set, if I'm to do the original Y outputs, you realize that if I'm to do Y dot, I think unique is going to, no, I think NP, let me see, import numpy as np. Okay, so np dot unique, and let me pass in yeah, let me pass in the y output over here. Oh, okay. Oh, I wanted to sum them. Um, I think there's a method. Oh, okay, summing everything. I just wanted to, so yes, we know it is 150, but then it is fairly distributed. So all the zero classes are, I've forgotten. There's a method we use to, I think it's count, something like that. Okay. So let me do dot count. Excuse me, just a minute. Hello. Okay, sorry for the interruption. I think, okay, let me just get some help over here. So this dots, okay, let me do, I think it's n count or something like that. Let me see. No, I think np dots, I think np dot, there's a method, I've forgotten. All right. I mean, I'll check that one up. Where we use, I mean, we can use to quickly count the number. So the point I'm making here is, okay, so imagine, yes, there are 50 of these classes over here. There are 50 of the other class, and also there are 50 of the third class. Together, they make 150. And we find out that out of the random selection, about 40 of one particular class was used for training, left with only 10 for testing. Clearly, we know that, okay, our model is not going to look too good, okay, for that particular class because it was not fair enough. So we would want to also investigate on all those matrices and see. Now, I believe let's look at the KNN classifier, and then maybe if we get some varying results, we can make good sense out of those explanations I wanted to give. So let me just quickly open this up. Now, the KNN classifier is an interesting one. And also in here, the concept of the model, and I mean the theoretical concept is very interesting. And I always use Kaswa to explain that concept, okay? Because as the name suggests, it is K nearest neighbor. So you are looking at the proximity you are to what we call the center or the centroid. So let's look at a typical example. a lot of people have the impression that Kaswa is in the Greater Accra region. And that's simply because within our minds, okay, we are kind of computing the classification of Kaswa in terms of which region it will fall in using K nearest neighbor, KNN. And the reason we are using K nearest neighbor is because Kaswa is closer to the center of Accra than it is to the center of the central region in terms of distance. So if you are to maybe not draw the map of Ghana, but then I think we've all seen Kaswa and I don't know which one. I'm trying to, okay. So if this is Kaswa, probably Accra Central, okay, will be here, maybe some few kilometers, and maybe Cape Coast is a little bit far apart. And if you are to do a clustering, or ordinarily, we are going to say that, okay, based on the distance to the center, Kaswa is most likely to be here than it is going to be to the central region. And it's not just Kaswa. There's a popular town in the central region called Dunkwa Ayamfre. Okay, those of you who know that will bear me out. Dunkwa Ayamfre is almost like sandwiched in between the then Western region. Okay, now there's Western North, so that part I believe is Western North. But then it is sandwiched between the Western region and the Ashanti region. So you find a lot of people, you ask them, oh, do you know Dunkwa? And people think it is either in the Western region or in the Ashanti region, because once again, it is closer to those capitals than, or to those centers than to its original place. I think this can be a good one because we are learning and also trying to draw inspiration from things around us. And I always prefer students to remember with examples of things around them so that it becomes very easy and relatable to check some of these things out. So let me just go to Google Map and see some of these things so that we draw inspiration from them. And then, okay, so good. So this is the center of, okay, so this is Cape Coast, okay, the center of central region, or the capital, not necessarily the center, but then the capital, okay. And then all the way, this is Palm Junction, Winneba, okay. We at, I think Kaswa will be somewhere here. Okay, this senior, okay, so this is Kukurubite, and then you can clearly see that this is Budumburam, so yes, this is Kaswa. Clearly you could see that the distance from Kaswa to maybe Accra Central, so let's just check the distance from Kaswa to Accra Central. Okay, so I'm seeing some 26.7 kilometers, okay, 26.7 kilometers. And let's do to Cape Coast. And this is about 114 kilometers. So, like I said, whenever we think about Kaswa, most of the time, of course, we know it is in the central region, but most of the time, using that inherent K nearest neighbor, we tend to think it's probably in the Greater Accra region. All right, and this is just for learning purposes. The Dunkwa Yamfre I spoke about. This Dunkwa Onofin in the Ashanti region. Ayamfre will be, yeah, this is the town I'm referring to. So Dunkwa Onofin, and you can imagine. No, I don't think this is the one I'm looking for. No, I don't think it's this one. This Inche, so yes, this is Dunkonofin, yes. So, like I said, this in the central region. But then look at Obuase. We know that Obuase is in the Ashanti region. Okay, so clearly you can see that Dunkonofin is very close to the Ashanti region and also very close. Those of you who know the Western region very well, I mean, this is that so now in the Western North, okay, and this Wasi Kropon. So this typically Western region and this typically Ashanti region, but then here you find Dunkonofin. And then if you are to compare this to its regional capital, look at the distance to the central region, I mean Cape Coast, it is quite a distance. And that's how people think whenever they are looking at things. And that's the inspiration we have with K nearest neighbor, because we believe that when we are putting things in cluster or when you're grouping things, similar things will tend to have some commonalities, okay? And those commonalities will draw them closer. So for instance, if you are classifying students into their various levels, okay? Level 100, level 200, level 300, and stuff like that. Well, we can say that, okay, the more courses you've taken at the university, the more likely you are to belong to a certain class. That's a general rule of thumb, except that you may have some outliers of some students who may be in their level 100, but then because of, excuse me, so they've failed some papers, so probably they have even taken more courses than, or they are going to end up taking more courses than their seniors in level 300 or something like that. I mean, it's possible. So those are the few outliers. But the point is, the similarities in the number of courses I have taken, if I'm in level 200, with the number of courses another brother of mine or another sister of mine in that same class has taken, will probably be the same. So, for instance, if we are making a prediction that, oh, okay, for the average level 200 student has taken about, let's say, 20 courses from level 100 to 200, and you want to make a prediction based on the number of courses a student has taken, the moment we put in 20 over there or 19, 19 is very close to the center 20. But then if that person has taken just 5 courses, then that person is far away. Probably that person will belong to a level 100 class, maybe level 100 per semester. On the other hand, if the person has taken, let's say, 60, maybe 60 will be too much, maybe 40 courses, then clearly that person is also far away from the 20, which is the level 200 class. So that's basically how I want you to picture some of these things. Because with K nearest neighbor, the whole fundamental concept is we want to calculate the distance we are to the center, the centroid, and the similarities that we have when data sets or data points are similar, they tend to be close to each other. And in order to explain that, I think last week we also looked at this. So let's go back and have that visualization of it to make sense out of what we have over here. And that was what you see over here. So yes, clearly you could see that because these ones belong to one class, which is the Iris Setosa, the blue markers, okay? Because they all belong to this class, you see that they are very close to each other. Unless maybe there's an outlier. But then if you have to pick the center of this, maybe the center is somewhere here. Let me just use the red marker to illustrate that. The centroid or the center is somewhere here, okay? So any data that is very close, if the data is maybe at this level, maybe a new data is introduced, the features are pointing to this particular point on the graph, it is most likely to belong to this blue class than probably the green class, because I mean the center of the green will be somewhere here. And if you have to check the K nearest neighbor in terms of distance, this one will probably belong here than it is to the green class. Okay. And even if you have to make a case for the yellow or the orange classes, its center is around here. And for instance, we are looking at the distance. So in terms of distance, it's most likely to belong here than here, and even far west than here. And that's what you see. And that's why I said with a lot of the misclassifications, you realize that with the Iris Setosa, you don't have so many problems. because of how distinct they are in terms of their uniqueness. But in the case of the iris versicolor, okay, the yellow ones, and the iris virginica, the green ones, you may have a lot of things being misclassified because you have a lot of them intertwined. And if you have to look at a distance, or maybe how do you call it? They are centroid, okay? You realize that this particular one, okay, let me just use this one as an example because these ones are very close as we have them over here. So with this particular one, this one is quite clear. We don't seem to have so many problems over here. But then this particular one, the center of the yellow is somewhere here. And I can probably say the center of the green is maybe somewhere here. So now the question is, if a new feature is brought in, let me use this one. A new feature is brought in, and then new feature is this brown one that I have over here. It is almost equidistant in terms of where it lies to both classes. So the likelihood of it being misclassified is higher than if it is brought somewhere here. It is very close to the centroid in this particular blue class. So having said that, let's see how we build a model out of the k nearest neighbor based on this fundamental concepts that we have come to appreciate with this particular algorithm. So once again, let's build something with the iris dataset. And like I said, I'm going to show you the other data sets where we can also explore and see some interesting stuff over there. So over here, I'm going to say from sklearn dot datasets. Let me quickly do it this way: import load underscore iris, and then from sklearn dot metrics, import accuracy underscore score. We also want to import the classification report over here. So classification, report. Then from sklearn dot model underscore selection, would want to import just a minute. Why is this not calling? Okay, so from sklearn dot model selection, would want to import train test splits. So train underscore test underscore splits. And then the k nearest model we get from scikit-learn. So we are going to say from sklearn dots. And this one, you're going to get it from one called neighbors. So let me just try and see if IntelliSense is going to help me over here. So neighbors, okay. I want to import, and what I want to import is the k nearest or the k neighbors. Okay, k neighbors classifier, k neighbors classifier. Okay. I'm hoping there's spelling because there's some capitalization of k neighbor classifier. Okay, I think this one is good. So now let's run this, and it says we have a problem over here. It says okay, obviously, and okay, so everything looks good. So now we can build our model and work our way through. So I'm going to say the data once again is going to be equal to this load iris that we are very familiar with. So the x underscore input is going to be equal to the data dot data, and the y underscore output is going to be equal to data dot target. So now that we have this, at least let's do a preview of this so that we are clear in our minds. Okay, so these are data for the x inputs, and let's do a y output. Okay, everything looks good. So now let's do the splitting. So I'm going to say x train x underscore test y underscore train, y underscore test is going to be equal to the train test split, and then we pass in our x underscore inputs, our y underscore outputs, and then we pass in the test size of, for instance, a 0.3. Okay, so now let's proceed straight to building our model because we know what to do. So this is what we need, okay, in terms of what we are going to use to build the k nearest neighbor. And what we are going to do is, once again, I keep on saying that most of the time the skeleton is what we need, okay, and then so the model is going to be equal to this, and now there are some parameters we need to specify over here, okay. Now intuitively, who can tell me which parameter do you think we need to specify over here? Any hand up? Okay, so let me give you a clue. Okay, when we're dealing with a random forest, we needed to specify the number of trees we want in that forest. Okay, so over here we are doing a classification. We want to cluster things, or we want to classify things into some neighbors. Okay, so one of the parameters that should just stick or come to mind is, okay, if that's the case, then we need to also specify the neighbors that we want. Now, it is very good we know this data set very well. We've done some visualization. So we can be very clear in our minds that over here we are dealing with two classes. And then also we know that, okay, this is a supervised data set that we have. So we also know that there are only there are only three classes in there. So those ones are very, pretty much straightforward. So what I want to do is, I would want to specify the n neighbors or the number of neighbors. So that's n underscore neib. I think their spelling of neighbors is this way. Okay, and let me just specify 3 over here. So everything looks good, and now I can do model.fit as we've always done. Then we do our x train, comma, then y train, and then we run this. So everything looks good now. Now let's do model.predict, and then we put in our x test over here, and let me have this as y predicted is going to be equal to this. So let me just have a preview of this and compare it with my y test, the actual one. Okay, I think this one too is looking very good. Almost, it's almost giving me 100%. Okay, except, okay, so there's some misclassification over here. All right, so at least this one will give us a better perspective in terms of the analysis I wanted to make. And also there's a misclassification over here. We see a 1, we see a 2 over here. And all right, so at least this one is going to give us exactly 100%. So this one will make a very good case for how some of these things are computed. So we can check the accuracy score. So the accuracy score, we pass in what was predicted vis-a-vis the actual, which is the y test. And now let me call this score, and now do a preview of score. So score is giving me a 95%, approximately 96. Okay, this one looks good. So with a 96%, we'd want to go beyond Jackson scoring 3. We want to see, okay, how many did Jackson miss, so that we can make an informed decision if this is actually what we are going to go with, because the accuracy is just giving us one side of the picture. So in order to do that, like you've seen previously, we are going to use the classification reports. So over here, I can see the, let me call this reports for now, and classification underscore reports. Once again, we pass in the predicted and the test. And if I'm to do a preview of this report, so let me do a printing of this so that it is nicely formatted. All right, this one is looking much better. So clearly you could see that if it was just about precision in terms of the first class, you realize that everything was 100%. The recall. So this is like Jackson getting 3 penalties. No, maybe this one is Cole Palmer getting 3 penalties and scoring everything. Okay. So this is how right he was, the precision. How wrong he was, there was nothing. So it was almost 100% perfect. And of course, the harmonic mean between the two is also giving us this. And at the end of the day, this is the support, the number of instances that randomly was selected. You realize that with the first one that we checked, okay, you see that everything is done randomly. So in this case, the number of instances over here was 13, but then over here with this new model that we are working with, it is 20. So things are randomized. All right. Now, in the case of the second class, okay, in terms of accounting, it was good over here in terms of its accuracy. The recall was this, and then the harmonic mean. Obviously, if we are finding the average of two numbers that are the same, it is this plus this divided by 2. So we are definitely going to end up with the same number. All right. And then it also happens that we also get this over here. Now, we also see some micro and macro averages, okay? And this is also going to help us. So clearly you can see that over here to the accuracy is being given to us. So over here we saw the accuracy and we said it was approximately 96%. Over here too, we are getting the accuracy showing as 96% over here. And clearly you could see that the macro averages, looking at all the high numbers, summing them together, in terms of precision, we are getting a 95%, the recall a 95%. Obviously, the average between 95 and 95 is still going to be 95. All right. Now, in the case of the weighted average, we have a 96% over here. For the recall too, we have 96. Obviously, the harmonic mean is also going to be 96 because 96 plus 96 divided by 2 is going to give us 96. All right. Now, in some models, the numbers will differ, okay? And based on the differences of those numbers, we can make informed decisions. So now the big question is, now which particular metrics is good? Well, it depends on one, the data you are working with and your objectives in terms of what you want to achieve at the end of the day with the model that you are building. But ordinarily, I believe, or I mean, literature supports that, okay, the F1 score kind of gives that holistic average. And normally when you have two extremes and you have the average, it is best, it is safe to go with the average. So over here, we can clearly say that, okay, the average accuracy, the accuracy is 96. This one looks so sweet. But then if I tell you that the F1 score for one particular class is 91% and another one is 93 and another one is 100, then we begin to look at, okay, so which one was actually, imagine maybe this particular class, the precision and the recall resulted in an F1 score that was probably, let's say, 20%. Then there's cause for worry because anytime a classification is made into that class, it could be wrong, it could be right. We need to further investigate or maybe do some few things to improve the performance of our model. And that's what we are going to cover the next time we meet, because we want to look beyond these numbers and get a proper view of how we can also correct things that might go wrong. Now, one of the last things I would also want to share with you, which also has to do with some matrices that we can also work our way around, which is I think the confusion matrix. Okay, so let me just bring that one over here. So I'm going to say from sklearn dot, I believe it's in metrics, I think so. Let me see, confusion underscore metrics. Okay, so this confusion matrix, and let me just say CM confusion matrix is equal to, once again, let's bring, we are checking for the predicted and the testing. So this is also going to give us some values that we can make sense of. So the CM is what we see over here. Now, these numbers may not look too appealing, okay? So you can plot this in a graph to see how things look like. So over here, we can get things from Seaborn. I think we've dealt with Seaborn. So I'm going to say from Seaborn, just import Seaborn as SN. And inside of Seaborn, we can use the heat map to actually plot this. So I can do SN dot heat map, and then I pass in this particular data, which is this metrics, okay, to get a heat map of it. So now when I run this, I get this beautiful illustration, okay? And I can make sense out of this better. Now, what I also want to do is I can do an annotation over here. So I can say annot, which is going to be the annotation, basically going to put out the values I want to see over here. If I say annot is equal to true, this is what we have. And let me just do, okay, so let me just import matplotlib dot py plot as plt. Okay, so plt dot show to get rid of those ones. But then we can also bring in the title, so plt dot title. And then we can say that there's a confusion metrics. And then we can also bring in the X label and the Y label, okay? So with the X label, what I want is plt dot X label. I can see this is the X, okay? So the X is going to be, I believe predicted. And then Control C and a Control V. We want the Y label to be the actual. So these are just labels we are passing out over here. It says X. Am I getting label wrong? Okay, I think so. Okay, so this one looks much better, okay, at least than what we see over, because this one does not really say a lot. But then we've plotted this using a heat map, and we can see or make sense out of this. Now, when we have a confusion matrix, what we are interested in is the major diagonal, okay? We want to have at least majority of the numbers appearing in the major diagonal. And this is what I mean. So let me just draw this out over here. Where is the other one? Okay. So let's say we have a binary classification problem. And I'm using binary because that one will make it a little bit simple for us to appreciate. When we have a binary classification problem, what we are going to end up having is, okay, we are either going to be correct or wrong. It's as simple as that. This for 3 classes. That's why we see 3, how do you call it? Boxes over there. But this is binary classification, so we just have 2. And now let me just label these ones very well. So let's say we have let me call these the actual class. Okay, or the actual side of the label, and also the predicted, just as we have over here. Now, for every prediction that was made, it can either be true or false. Now, if it is true, over here, look at this. So in this case, the assumption is, oh, I cannot hold this. Okay, so let me just draw this down a little bit in terms of how it looks. And let's assume the class names, okay? So this is class 0. and this is class 1. Maybe male and female, or good or bad, or spam or no spam. You can imagine. And this is also going to be 0. And finally, this is also going to be 1. So this is what we are trying to say. Let's assume 0 is spam and 1 is no spam. Okay. So 0 is spam, 1 is no spam. Now, on the actual, if the thing was a spam and it actually predicted that it was a spam, then it should fall in this quadrant, because this is a spam and this is also a spam. So the actual is a spam and the predicted was a spam. So it should fall in this quadrant. Good. Now, if it was no spam and the predicted was also no spam, then it should also fall in this quadrant, because the actual is no spam and the predicted is also no spam. So it falls in this quadrant. Now, in the case of these ones, okay, so this is a major diagonal. And that's what I said, or that's why I said that's where we are most interested in. Now, in the case of the other diagonal, you realize that, okay, this was an actual spam, but it was predicted that it was not a spam. So you see that the actual was 0, but then the predicted was 0. So that means there's a misclassification over here. We need to take records of that. In the case of this one, we could also clearly see that, okay, this was not a spam, but it ended up predicting that it was a spam. So over here, we also get a problem we need to resolve. Now, what happens is, okay, what we see based on our descriptions of things, okay, because some of these things can change. This will be a true positive, okay, because it was spam and it was also predicted it was a spam. So it was true and it was positive. It was a spam, basically. And this is also going to represent the true negatives. So Tn. And over here, it was not a spam, and it also predicted that it was not a spam. Okay. Or maybe I think the spam and not the spam may not work in this context. So let's say a disease diagnosis system, okay. So disease or no disease. So let's say the 0 is disease and the 1 is no disease. Okay, so this is true positive. It was true that the prediction was right, and it was actually positive that the disease was there. That's what we see, right? So the actual and the predicted are intercepting. And over here, this is a case where it is true that you didn't have the disease. Okay, so it is true, and the COVID test is negative. So the actual was you don't have COVID, and the predicted also is telling you that you don't have COVID. So this is a true negative. The test result is negative and it is true. Good. Now, in the case of what we have over here, this is going to turn out to be a false. This one, okay, so this one was positive. Okay, so it's going to be a false positive. And then this one is going to be a false negative showing up over here. So at the end of the day, the question is, okay, with this one, it was trying to predict that it was positive, but then the actual is saying that it is false. So even though you are predicting it is positive, but then the actual says it is false. And over here, it was trying to predict that, oh, it is negative. It is not negative based on the prediction over here, but the actual is saying that, well, it is false in terms of that. Now, if we appreciate this very well, that's exactly what has been expanded over here. Because we have 3 classes, that's why we have the 3, quadrants, kind of, okay. And over here, all that this is saying is, okay, for class 0, which is the iris setosa, remember we had 20 over here, and that 20 is nothing but the number of supports we have over here, the number of instances that were used in the computation in terms of trying to do the prediction and also doing the testing. So over here, we have 20 over here. And it turns out that all the 20, which was in class 0, obviously was in class 0 as in the predicted over here. So everything looks good. Now, in the case of the ones we have over here, we clearly could see that, well, the actual of the second class, okay, which is the class 1 over here, was, I mean, cumulatively, we had a support of 11. Now, out of that 11, we realize that 10 of them were predicted correctly. So it is 1 over here and it's also 1 over here, so they intercept. But then the other one, and this is where you can actually see where the other one is going. You realize that the other one ended up being misclassified into class 2. We see the same thing over here. We had cumulatively, we had 14. But in the classification, we realize that, well, 13 were classified correctly, and then the other one went into the other class. Remember, it didn't go into the first class. So, and that's what we see over here, like I've shown over and over again, because the first class is the Aries Setosa, the blue ones. Those ones are, they don't have any problem when it comes to we trying to separate these ones, okay? They are very close to each other. They are linearly separable and very wide apart from the other ones. It is only with the Aries virginica and the Aries versicolor that are a little bit intertwined. So if there's going to be any classification, I mean, misclassification, those are the ones we should be paying attention to and not pay so much attention to Aries Setosa. And that's what is being is becoming evident over in terms of what we see. All right. And I believe as we build other models, we are going to come back to this and we are going to see how sometimes it becomes a little bit complex when we are trying to look at some of these matrices. Now, finally, let me say this so that I give you a little bit of an assignment so that you just play your hands around some of the things that we've been building our way through. So with the assignment, it's very simple, okay? I would want you to do some exploration yourself in terms of the data sets I'm going to give you. And this data set is the breast cancer data set I spoke about. So let me see, from, it's also in sklearn, okay? So from sklearn, when I say import data sets and do data sets dot, okay, so we have the, okay, so this is the breast cancer, and there's one for diabetes, there's one for handwritten digits, which we are going to come back to when we start building convolutional neural networks and stuff like that. And there are quite a number of other data. There's a wine classification data set that we can also look at. And then, yeah. So those are the major ones. But then let's look at the breast cancer data sets. All right. So dataset.this, and let me save this in a variable called data. And now let me do a preview of data. Of course, this is what I want you to do. So over here, you see that we are having some, I mean, looking at this data column, okay? And then we're having the targets. So over here, clearly, we can make sense of the fact, okay, this is going to be a binary classification, okay? So what I want you to do is, of course, this part of research is, okay, looking at the target names, let's look out for the meaning of, and I believe some of the biomedical students and even those who are, I mean, maybe biology can even give you a clue. That's okay, malignant and then benign, okay? In terms of the 0 and 1, okay? So the 0 will definitely be this one and the 1 will be this one based on how it has been structured over here, okay? And then there's a description over here that we can look at. So let me see if, okay, so let me just grab this and do data dots the description and see. And let me see if this one gives us anything better. Okay, I think this one looks good. So we can look at the description of it. So this is a breast cancer Wisconsin diagnostic data set. All right, so the number of instances is what we see over here. And the attributes, okay? 30 numeric predictive attributes and the class. So there are 30 attributes and then a class. Okay, so we can use this for classification. And the attribute information is what we see over. If you have the radius, okay, that's the mean distance from the center to the point of the perimeter, and then the texture. Now the standard deviation of grayscale values. So I think the whole storyline of, or the history behind this data set is some, how do you call it? Images of breast were captured, okay? And of course, some had cancer in there, others did not. And these were the values that were extracted. So for instance, the radius of the breast, the texture, the perimeter, the smoothness, the compactness, the concavity, the concave point, the symmetry, and I believe the biomedical people will give us a little bit more information about that. Okay, so it says the mean, standard deviation, or the standard error in the West largest. Now, mean, the three West values, blah, blah, blah. So the classes are what we see over here, and the statistics. Okay, so the mean radius, the mean. So there's a bit more of information that we can look at, okay? And yeah, says emitting attributes, none. So this one is very clean. We don't have a problem. Now the class distribution, it's a little bit biased, but at least we can manage with this one, okay? And then the creator of this is this gentleman in 1995, and is also in the UCI machine learning dataset repository. You can check it out over here. And so what I want you to do is kindly do a little bit reading on this, okay? Now, just build a model with the algorithms we've discussed, at least up to this point, okay? So all that I want you to do basically is to do a research on this, come and do this, load it this way, data.data, get this, okay? And then maybe do .ship or something, just to familiarize yourself. Okay, so you were told over here that it has 169. You've actually confirmed it over here, 169. Okay. And we also told that the number of attributes are 30. So we can also confirm that it is 30 over here. Okay, so that's looking good. And we're giving the names of these attributes. Okay, so we have the radius mean and stuff like that. So we can also check those ones. If, for instance, I'm to do, maybe grab the first row. So everything you see over here, I believe there are 30 of them. Okay, so I think 1, 2, 3, 4, 5, 6. Okay, so you have 6 on one row, and you have 1, 2, 3, 4, 5. So definitely 30. And with every particular data point that we have over here, this, for instance, the 1.79 times 10 to the power positive 1 is representing the mean radius, technically. Is that okay? And then the other ones, what do we have? This one, 1.03 times 10 to the power 1 is also representing, I believe, will be the texture. And it goes on and on and on, okay? So let's build a model with this data set, do some classification. So what I want to see is, let's build one for the ones that we've seen, okay? All these ones, okay? So for instance, decision tree, random forest, support vector machine, naive Bayes, and KNN. And let's try and document it very well. Imagine this is your final year project. You'd want to document it very well. You want to save some images, and let's have it nicely packaged so that at least for some of you who have GitHub repositories, you can even put it on your repository just to boost your confidence into building some of these models. All right. Then, of course, when we meet, we'll check, and maybe some few people will do a presentation of what they had, and we'll have some discussions. Okay, so please, any questions? Okay, so in the absence of questions, Dr. Mills, please, I'm done.
Yeah. All right. Okay. So thank you very much, Ken. So at least now we can see that we are done with the basic classification algorithms that are used in any research relating to machine learning. Any research related to machine learning, these are the algorithms that are used in that, whether you want to publish the work or so. These are the key algorithms that may come up if you have done something that people want to check why you selected a particular algorithm and what informed that decision. And it's really based on the performance measurement. So now that we are done with this, Friday, God willing, Friday, maybe we may have to discuss whether you want us to do it virtually or you want us to do in person. If you want us to do in person, then we will meet in the Huawei lab. Then we'll maybe individuals who have done each of them, they can show us what they did and their results. Maybe one model after the other. So 1, 2, 3, 4, 5 algorithms.
Okay.
Please, the way if you want us to go virtual, then you can put on a platform for the Friday. Otherwise, then we'll move on to our in-person. Then we'll see what. Then if there is any other thing, we will wrap up with the supervised. And then if we have the time, then we'll start with the unsupervised. Some basic concepts about the regression models. Please,
Okay.
are we okay on that?
All right, sir.
Okay. So on that note, we wish ourselves a good week until Friday. Okay.
Okay, sir.
Thank you to everybody. Okay.
You're welcome, sir.
And Ken and Sami, thanks so much for the presentations. Okay.
You're welcome, sir.
You're welcome.